Okay, good morning. I'm Johnson from CADVision. Today I want to share you about a webinar of the topics of how can I make the simulations calculations time shorter. I'm Johnson Yaps from CADVision. Okay, so now everyone here. Okay, so now due to the time problem, I want to start my webinars now. Okay, today my topic is how can I make the simulations calculations time shorter. Okay. So if you have any problems or any questions or any inquiry about my webinars or my sessions, you can comment on here. I will look for your chat, or I will look forward for your chat and answer your questions. Okay. So now, let me hide this. Okay. Now my webinar session is how can I make the simulation calculation time shorter. I will use SolidWorks flow simulations for my presentations today. Okay. Okay. Actually, how we can make our simulation times is better. Actually, it all depends on the meshing process of the simulations. As you know, all knows from the understanding about our simulations is based on the meshing process. Meshing process is the method of dividing the 3D models into thousands or hundreds or tens thousands of the small finite element units and calculate it or solve it one by one. Inside this flow simulation, SolidWorks flow simulation, it can generate up to 1 million or above of the finite elements units. And inside flow simulations, it is present as the cubes. It is divided into cubes by cubes. And you solve one by one and make your calculations better and accurate. So as you know, every computer has support a maximum amount of meshings. And due to the limitation of the computer, we have to optimize the meshings and to save our times. As you saw, the amount of meshing is increased, the accuracies also will increase. However, due to the amount of meshing is increased, the calculations times will also increase. Let's say now if I have 100 of meshings, it takes around 1 second to 2 seconds to generate out the answer. However, the answer is not so accurate because the 3D models have divided into 100 blocks only. However, if I use up to 1 million of the cubes, let's say I divide the 3D model to up to 1 billion of the cubes, the accuracies will increase largely. However, the calculation time will take us a lot of times, maybe needs around 1 hour or maybe it's around 1 day. So in order to optimize our meshings and we have considered to the performance of the computers. Maybe some computer can support up to 1,000 of the meshing only, or maybe some supercomputer can support up to 10 millions of the meshing. So this webinar is to teach you how to use the SolidWorks flow simulations to optimize the meshings. Okay, now I'll ask you, if your computers only can support maximum up of 2 millions of the meshing unit, how you plan these meshings? How would you mesh them wisely to make it a most efficiency way to generate out your accurate answer? Let's say now, if you had this one at the right bottom here is electronics boards, and you see here, I have used 2 millions of the meshing unit to mesh my products. to divide my products into to my 3D models into 2 millions of the box. At the left here, this is a not very good meshing, and the right here, this is a very good meshing. As you depend on here, these two meshings is considered of 2 millions of the cube. I have divided this meshing to consider to 2 millions of cubes. However, if you see here, the meshing is different. And you see there at the left side here, the meshing is very even and no big size or small size, all is inside the same size. However, at the right side here, all is not same size. And you see around here, the size is bigger, and around near the electronic components, the size of the cube becomes smaller and smaller. Why I say this is a very good meshing? Because the meshing is depend at around here, there is no electronic components. Why we need to focus to calculate here? There's no point for us to calculate here, so the meshing here is only 1, 2, 3, and now 20 meshing here only. However, when the region is near the electronic components, the meshing start to concentrate already. And you see here, the meshing is around 1000 to 100, but around here is around 10 to 12 or 10 to 20 only. So this is a powerful ways of the meshing. For these powerful meshings, around here, the meshing is more nicer and make our calculation times nice. However, in here, there's only evens and not very nice, because at here the box is quite smaller. Around when the region is near the electronic components, the cube is divided more largely, more small and become very small cube. But around here still a big cube. So I can say that for the regions around these electronic components, the calculations will much more better than this one. Okay. So now I will teach you how to make the meshing focus on the electronic components and make our meshings better and better, and make a more accurate flow simulations. Okay, so today's agendas, we have divided into 5 topics: the model simplifications, the remesh, the local initial mesh, the sub-modelings, and the transfer boundaries. For the model simplifications, we will simplify the 3D models. Let's say the fan, we will assume it as a solid and make it assume it as the fans inside our simulations. And for the remesh and inside the 3 model simplification, we also insert all the heat source, all the boundaries, air ins, air outs, all the fans inside it. So for the second topic, the remesh, I will focus on the meshings, as just now, teach you how to focus on the regions of the electronic components and mesh it well. How to focus the meshings, the cubes on the surface of the electronic components. And the third side is the local initial meshings. These ones I will focus on the local studies. Let's say this has the global meshings, but however, I still can focus something like the heat sinks or the small electronic components. I want to focus on the meshing on it, so I can use this one, local initial meshings. The fourth one and the fifth one, the topic is the same actually, is the transfer boundary. Let's say I only need to study one component of this one electronic board. I no need to generate out the answer or the flow simulation of all the electronic boards. I just need to focus on the electronic components only. They save a lot of time to study this. Okay, so now, but not wasting the time, I focus on the first one, model simplification only. Okay, so now I go I exit my slide first. I go to my SolidWorks programs. As you see here, this is the electronic board. We call it of the power supply, portable power supplies inside SolidWorks. And now I want to use these 3D models to set up my flow simulation study. Okay, as you see here, I already created a flow simulation studies inside these tabs. Now I will carry out the model simplifications. Okay, I will see here, this type is I make use of the change the transparency. Okay, inside my models, there's a lot of electronics. I want to introduce about my electronic board first. In my design of my electronic boards, it consists of a fan, as you see here, a fan, and an inlet here, hole here to allow the environmental air to flow into my electronic boards. And there is a lot of electronic boards which consists of the capacitors, this one the generators, and this one the heat sink. This is a heat sink which help us to diffuse out, to emit out the heat generated by all these electronic components. The air will flow in from the inlet here, flow here, and is flow through all the electronic components, and it absorbs all the heat released by the electronic components, and it flow out from this fan. Okay. Now I want to set up all the flow first, all the flow simulation data first. I will see here the input data. We can set up all the components here. I will see computation domains, since that there is the area of the study or the region of the study. I will see this is the region of our study. That is automatically set for us already. And inside the solid materials, we have to insert all the solid material into it. Inside this flow simulation study, all the components still didn't have the materials database, the materials information. So we have to manually input it. LC, if you know how to use the SolidWorks, you know that every component, I open back the design tree here, every component has the materials, like this one, the PCBs components, this one the components, the materials is all set. Or this one, the pins, all the material is set already. All I need to do is I just to insert all my material into this solid materials. I input into for my 3D models. So I use the tools. I input data from models. Okay, as you see here, from the 3D models, all the data is input here already. They is scanned all from all this data, material data is scanned from my 3D models from here. All my 3D models, as you see here, all have the materials. If you know how to use SolidWorks, you know that all here have their own material. All the heat sink here have their material. Okay, so now I have really scanned all the material inside my 3D models. And you see all the material is come out already, and I just click import into my flow simulations programs. Okay. Now, as you see here, okay. Now, as you see here, all the solid material is already input into all the information already input into my flow simulations database. If I edit it, then you will see all the information inside. ABS and all the informations. ABS. Item properties, you all the information inside it. All the information required by this flow simulation, it will input inside this. Okay, so now I successfully import all the material information already. The next time I want to set the boundary condition. Boundary condition actually is the is the way to connect this internal flow study to the outside environment. This is the closed environment that is not connected to the outside environment. So I need to set the openings to connect to the outside environment. So I set the boundary. I insert a boundary. For this case, this is this phase. You see here, this phase is the phase that connect to the outside environmental air, which the air flows from the opening into this electronic board. Okay, and this phase I set these two phase. Then I will set as the environmental pressure to 25 degrees, 25 Celsius. It means that after I set it, the air only will come in from this hole. I tell this flow simulation study that the air is come in from this hole with the environmental pressure of 1 atm and 25 degrees Celsius. So the inlet of the air, the information I input already, I want to insert a fan. I will see here, this is a fan. If I hide this face, if I hide this, there is a fan here. However, this fan, I just draw it as to let us know there is a fan only. There is no function of it. I just let you all to know this is a fan only. Actually, inside the flow simulations, we had to draw another fan dummy. Just now I draw it already, and this one is the fan dummy. I will assume this one as the fan inside the flow simulation. As you know, the flow simulation study, it cannot detect this one, the fan. Although I draw this fan out, it cannot detect this is a fan. It's only know that this is one of my electronic components of something else. However, as just now we see, I draw another plan to it. This is a very simple plan. It only can, I want to let this flow simulation study to recognize by as this solid body is the fan. So the fan here, I can insert fans. Okay, so and you see here, I can choose this face as my fan. This is the model simplification to let flow simulation to know that this is a fan. So I choose this face. I choose external outlet fan. Okay, because this is the outlet fan, will connect to the outside. Because here will show that inner fans, outlet fan, and the internal fan. Now I choose it as an external outlet fan because this fan is located at the outlets of this electronic box. So then the next time I will choose the type of fan. I will see here inside the SolidWorks database there is a lot of fans information, a lot of type of fans. I choose at here the series 600 and 605L. This is the fan. And you see from the create edit here, this icon here, inside SolidWorks there is a lot of data fans database. If I choose this 605L, this type of the fan, all the information of it and the table curve, the fan curve will all already inside the SolidWorks database. Now I just need to choose this and set as my fan for this case. Now as you see here, this arrow shows that the air will flow out from this surface or this fan. Okay, so now the next thing is I want to set the heat source for this flow simulation study. As you know that this is only the 3D models. The flow simulation study didn't know which one has generated the heat. So we have to insert the heat source for it to recognize it. So from the input data here to the heat source, okay, so I insert the volume source, I click all these capacitors, and I let it as the 10 watts. So as you see here, this flow, after I click OK, deep flow simulation will know that all these 5 capacitors will generate the constant heat of 10 watts inside this study. So I click OK. Now for these 2 transistors, I add another heat source. For these 2 transistors, I make it as the 5 watt. And these 2 heat sinks, as you know, this is the heat sinks. I make it at the 4 watts. Okay. Now the other component, I assume there is no heat generated out. I just assume this thing. I just choose just now the component have the heat generations. Now the heat source, the heat generation source, we have already input into this data. So now we have to start to mesh our models. Now I carry out to the meshing, remesh inside outside. Okay, I carry out this into the topic 2 called the remesh. Okay, now before I remesh, I want to generate out the raw meshing first. I'll see here. I can calculate the initial mesh. I can set up the initial mesh first. Okay, it takes some time to generate. Okay. Now as you see here, the initial mesh here, it shows the number of cells across x-axis, the number of cells across y-axis, and the number of cells across z-axis. As I meant when I show the basic mesh, I'll see here, these models will divide it into hundreds of cubes. As just now, this is called the meshing. As you're familiar for the SolidWorks flow simulation, you will know that how this meshing is working is SolidWorks. I can adjust the size of meshing. Let's say now this one I adjust to 40, double it 44. This one I double it 12, and then double it to 56. As you see here, our meshing is also double also. All the cube is small to 1 time already. 1 time smaller already, the cubes. I change back to normals. 6 and 28. Okay, it changed back just now. What I do, I just need to click OK. And run the meshing. Due to this meshing runtime is too long, I straight away open my meshing file. This one I hide it first because this is just a preview. I not yet mesh it. I need the time to mesh it out to run the meshings. So now, just now, I hide all this meshing first because since I show the basic mesh already, I can hide it. There's no more meshing already. So now I run it. However, this, oops, sorry. I not yet hide just now. Oops. Okay. Okay, I create the one show the basic meshing first. So in order not to confuse, then now in order to not waste the time, I load the result file from my I already done all the result already. Now I only need to show all the result. Because this result maybe make us 4 to 5 minutes to generate out the meshing. So now I only load the result I create earlier. I already prepared earlier. So as you see here, I show the cut plots. Yeah, if you're familiar to the SolidWorks flow simulation, you will know that what is the cut plot. It will show all the cut plots. This is the cut plots. Now I use the cut plot as the tool to show my meshing. I will see here, this is the meshing. This is not a very good meshing because near the electronic component, there is no more smaller cubes meshings, and this is very even. The meshing is very even. So now we require the remesh to mesh our products better. Okay, now This is the first meshing. And you see now the initial mesh here, we still got another meshing, another improved meshing setups. Okay. And you see, okay, as the initial meshing, these are the setup menu here. There is a lot of improvements and changements called the solid fluid interface, the refining cells, and the narrow channels. This solid fluid interface will help you to curvatures, refinery levels. Help you if the solid have the curved surface, it will automatically, let's say like this capacitor, it have the curvature surface or the circular surface. This is called a cylinder or the circular surface. If I increase this level, it will automatically detect this surface and increase the meshing or increase the cube around this surface. So as here, it got three types of enhancements called the solid fluid interface. This one to increase the surface of the curvature here. And refining cell. This one we can choose we want to refine the fluid cells or the partial cell, or the solid cell. The fluid cells means that these cubes, all the cubes is centers located on the fluid only, which contain fluid only. This is called the air or the fluids or the air components there. Or the partial cell or the solid cells mean that the cube is located inside all the capacitor or this something like this one, the heat sinks or inside fan. The cell is considered as the solids. You know what I mean? Means that the fluid cells mean that the cubes consist only fluid only. The solid cells mean that the cubes consists of the solid only. The partial cells means that the cube consists of the both of the solids or the solids or the fluid cell, something like this. I'll show you the examples, and you see here this cube. This cube is the fluid cell. This cube is the partial cell because it consists of the solids and the fluids. And for the solid cells, I cannot show here because it is blocked by this capacitor already. Actually, inside this capacitor also have the cube. However, the cube only consisted of the solid cubes. So you have defined as the fluid cells, the partial cells, and the solid cell. Okay, I hide the basic measurements. Now I want to show you how this curvature in refinery level, this solid fluid interface here, can enhance our meshing. So now I increase the curvatures, refinery levels. The small solid feature I also increase. This is all due to detect the small solids, like this one we can see as a small solid. And this now we also can consider as a small solid features. If I increase the level, so it will detect this one and this one. You automatically detect it. And the curvature refinery level, I also increase it to level 3. Okay. Now I click OK, and I run this meshing. Now to not waste the time, I already prepared these meshings. I just look for it and look the result. Now I look the result. I just prepared earlier. Okay. Now you see that the meshing is already changed already. And now show the meshing. Okay, so now you see that, I see from the top side here. Now you see that the meshing will lastly different with just now already. And you see here, near the curvature surface, near this one, the capacitor, the curvature surface, there is more meshing already. And now I want to show you what is the I want to explain again about the fluid cells, the partial cell, and the solid cell. This is the fluid cell that you see here. This is the fluid cell. You see my mouse here? This is a fluid cell. This is a solid cell. You see here? This is all is a solid cell. And this one, I increase further. This is the partial cell. Okay, I repeat again. By using this one, using a pen. This one is a solid cell. This one is the fluid cell. And this one is the partial cell. Okay. This is the solid, this is the fluid cell, this is the partial cell. This partial cell consists of the solids and a bit of the fluid. And for this cube, this is a bit of the solid and a large of the fluid cell of the fluid. So this is called partial cell. Okay. So now like this. Make it drawing. Place all drawings. Okay. Now as you see here, this is quite better already. As now I show it, I make a conclusion inside this slide. I will see here this is the before the curvature phase focus. Just now I focused at the curvature phase. This is the before. I mentioned this is the first time I show you one, and this is the just now I show you one. As you see now, I focus on this area. I will see here there's no focus on the curvature surface. And this one, we focus on the curvature surface. I will see near the surface, curvature surface, there is a small cube here. This will make the calculation quite more better with this one. If compared with this one, this calculation will more accurate and more better result will come out. Okay, now I want to focus on the partial cell focus. Okay, now as you see here, I just open back for the initial mesh setting there. Okay, now I open back here. Just now I use this tab, the solid fluid interface, this tab to enhance our meshing. Now I don't want it. I just change it back to zero level, and assume this is no enhancement. Now I focus on refining cell. As you see here, just now I teach you already, got the fluid cells, the solid cell, and the partial cell. And here we can choose. We want to refine which cell. Refine means that make the cube smaller. This one, let's say this one, if I increase each one level, maybe one cube of the fluid cell will become 4 cubes. One cube is divided into 4 cubes. And this one, it will be maybe divided into 16 cubes, because you say that one cube is we make a small one times, it will divide it into 4 cubes. Okay, so now I choose to refine fluid cells and partial cell only. So why I want to refine this fluid cell and partial cell but not solid cell? This is because this study is the flow simulation. It's only focused on the fluid cells and the partial cell. There is no more focus on the solid cell. It's because inside the solid, there is no flow. There is only flow at the fluid cells and the partial cell. I will see here, there is only flow in this area only. In this area only. This area. But inside the capacitor, there is no flow. So there is no point for us to enhance there is no point for us to enhance the solid cell. There is only got point we enhance the fluid cells and the partial cell. I repeat, do you get I meanings? I means that this is the flow simulation. All the study, all the calculation is on outside the surface, outside the solid. Inside the solid, like inside the capacitor, there is no point for us to enhance the meshing because there is no study inside. There is only study at the outside fluid area. So now I just enhance the fluid cell to level 1 and the partial cells to level 2. Okay, I repeat, I enhance the fluid cell to level 1, the parcel cells to level 2. I click OK, and I click run as just now. I run it. Okay, same as just now. I just load the result. I load this result first. I load the result from after I done this meshing. This I done it before already. I just load it to let you to see more faster. Actually, this meshing average time taken to generate out is 5 to 10 minutes. However, now I just done it and let you to see immediately. Okay, this is the result I done earlier before this webinar sessions. Now I just make the top views. I will see here, now it's changed a bit already. Okay, this is not very good. If I see from the plants, now I see from the plant is better. I can show you how this plant, how this is very important. Now I focus. Okay, now I focus in. Now I change into isometric views. I focus in this capacitor study. Okay, so now these meshings, I just move back to here. And now I change the transparency. Displays. I change the transparency of these models. Okay, change transparency already. To make you to see this result more clear. Now you see around this surface here, you will see that. Oops. Okay, around this surface here, you can see that. Oops. I think displays the real one is better. Sorry. Okay, now you will see that around this surface, this capacitor surface, there is more meshing if compared to the just now the air around the fluid cell here. As now, if I see the slideshow, I've concluded it as a slideshow here, to make you all to see better. This is the meshing of the normal one, of just now the not yet enhancement, and this is after the enhancement. You see, if I focus on this capacitor here, you will see that there is a last change. For the normal ones, there is no enhancement. All the cells is normal and evens. But after the enhancement, after the partial cell focus, you see that all the cell at the partial here is already become smaller. The cube here is become smaller. So when the analysis touch this surface, the analysis is more accurate and more efficiency. I will let you to see that. I will ask you the very common questions. You think that this is more accurate or this is more accurate? There's only one answer only. This one is more accurate. Okay, now I focus on my third enhancement. This is the narrow channels. This one I hide it first. I unload the result first. Okay, now I proceed to my third enhancement, which enhance the narrow channel. Okay, as just now, we proceed to the curvature already, curvature enhancement. The second one is about the enhancement of the fluid cell or the partial cell. I just uncheck it. This one, the curvature, I make it no more enhancement. This one, I also uncheck it. I make it 0 first, 0 level, and uncheck it to make sure that this enhancement is no influence about this later my result. Now I focus on my third tab, the narrow channel. Okay, this way is narrow channels. Actually, I want to show that. Let's say now, this I can consider this and this way is a narrow channels. Or this way and this way maybe is a narrow channel also. And this way is this way I also consider as a narrow channel. The narrow channel is see how you define the narrow channels. Actually, is see how you define the narrow channel only. So now we can help let this flow meshing to help automatically define the narrow channel in this study. I define the narrow channel in this study as 10 mm. This to this, if it is 10 mm, I consider it as the narrow channel. If here to here is not 10 mm, I not consider it as the narrow channel. You get what I mean? It means that if I from here to here, I consider have the narrow channel, then I will increase the enhancement for it. From here to here, there is no more enhancement for me because I not consider it as a narrow channel. All of this I can set from here. I repeat, I can consider here for the narrow channel and here didn't have the narrow channel. Let's say here is less than 10 mm, I consider it as a narrow channel inside this study. Here to here is, you see here to here is more than 10 mm already. I don't want to consider it as a narrow channel. I only want to enhance here, I don't want to enhance here. So, I'll see just now, I can set from here. Now for the enable narrow channels, I set the level. I will see here to enable the minimum height and enable the maximum height. For the maximum height, I set it as 0.0001 or 10 mm. After I set this maximum height of 10 mm, it will calculate if this one over 10 mm, you will not consider enhancement, and this one if less than 10 mm, you will consider the enhancement. Okay. Then you can set how many cells across the channels. Let's say these channels, I can set it to, if I set it at 5, then it will show that from here to here, there's 5 cells. You will insert 5 cells across this narrow channel. For the minimum ones, I just set as 0 at 0 meter, so that all of the narrow channels smaller than 10 mm you consider as narrow channel, and this one the meshing will enhance it, make more cells and focus on it. And click OK. After the running, I will note that this way all will enhance, but this way will not enhance. And now you see that inside here, it will lastly enhance. This is called, we will focus on here. All here narrow channel will be considered. Now, okay, I just run it and meshing. As same as just now. Now, as same as just now, I just look the result. I just look for file. Okay, now I already prepared narrow channels, the result of narrow channels more than 10 mm. Now let us see our result. Okay, now I see from the tops. I show the result from the top. Now you will see that our version is quite better already. Okay, all here didn't have narrow channel one, didn't have the enhancement. From here, he detects the narrow channel is less than 10 mm, that's got the enhancement ready. I will see here got enhancements ready because here is less than 10 mm, and even here or inside here less than 10 mm. Now my question, I have the problem here. I will see here, although this here didn't have less than 10 mm, there's no more enhancement. Because this narrow is too small already, this my levels just now I say here, the initial message just now I open back the setting here. Okay, and I choose that the narrow channel tabs. This level is not enough to enhance it. If I increase the level to 10, level 9, I have sure that this will be largely enhanced. However, it takes a lot of time to meshing it. Maybe it takes around 3 to 4 hours to meshing it. That is not a good meshing because it wastes a lot of time for meshing. Although it is a nice meshing, but it takes a lot of time for our meshing. So later I will teach you how to solve this problem by using the local initial method. But now I will focus on this narrow channel first, because now I not yet teach you how this narrow channel first. Later I will focus on the local initial mesh. Now as you see here, these narrow channels. Now you will not see how different, but now I will show you the slide in not focus, and you will show the difference already. You will know how the difference already. Now this is a summary of just now the narrow channel focus meshing, remesh. You see here, this is the normal one, and this is the after I use the narrow channels to enhance it. And this is just now the partial cell one, partial cells focus one, and this one is a narrow channel focus one. You see from the focus here, you will see that when this one, the narrow channel is more than 10 mm, is 11 mm, and this one is 9 mm, only this way is enhanced only. This way didn't enhance anymore. Okay, so by using just now the methods, you will know that how we can enhance it. You get it? By using this method, you can set which way you want to enhance, which narrow channel you want to enhance, which narrow channel you don't want to enhance it. So now you can plan your meshing very well. Let's say you have 10,000 meshing. You must plan it very well. By using this narrow channel, you can plan it very well. Okay, done. Now next one, I will focus on the local initial meshing. Okay. Now as you see here, this is a global meshing. This is a global meshing. We call it as a global meshing. You see just now I open back the initial mesh here. Okay, this is called the global meshing. Okay, now I want to mesh this way, focus on heat sink here. I will see just now the heat sink here, there is no more, the meshing here is not nice. I want to focus to meshing at here. So I can create another local initial mesh. This is at the input data here got the local initial mesh. From here we can create another new local initial mesh. As from before I want to create a local initial mesh, we have to build another dummy body. Just now I will see that here. Inside I change to the model side. Actually I already create a dummy body, I just show it up. I will see here, this is a dummy body. This is a dummy body. If I just change the transparency, you will notice that this is the dummy bodies. It covers all the regions of these two heat sinks. Now inside the SolidWorks flow simulations, we can use the local initial meshing. Then I choose these two dummy body from this models here. I choose this dummy body. As you see here, these two dummy body is selected already. Now I can choose to disable this solid components because this dummy bodies is just a representation, it's not a solid body. I want to repeat here that these two dummy bodies is just a representation of the volume or the region. It is just a box. This is not a solid. It's not considered to calculate inside the flow simulation. Means that the air will still flow across the boundary. It's only a boundary, a box. The air will still flow through the boundary and insert in and flow through the heat sink. It's nothing. It's just a representation to let you to know that this is a region around that. Okay, so I can focus on, you see a very similar, a very familiar setting is around here. This is the settings focused inside this toolbox only, but not all the world's models. I repeat, this setting is for this region only. This region is this toolbox. Means that all I setting here, whatever I set, all the meshing inside here is influenced already, or only. The global meshing is not influenced. This, so I call it as a local initial mesh. Means that if I repeat, if I change anything, I increase any enhancement here, like the refinery cell, refined cell, part cell, enhancement, and then enhance the meshing here, only these two meshings, these two regions inside these two regions will be influenced. The meshing of the global will not be influenced. Okay, now I show you, but not wasting the time, I show you the result. The curvature, there is no, and because there is curvature here, I use the solid fluid enhancement, the curvature, I insert to level 2. And the refinery cells, the fluid cell and the parcel cell, I want insert to 3 and one insert to 4. And the row channel, I think there's not a point, but I just increase into level 2. Okay. Now I click OK. I rerun it. Okay, sorry, due to some problems. It takes some time. Okay, now let us rerun it. Rerun it. Okay, mesh it again. Now, assume I already mesh it, I show the result to you. I already done it before, the results with the same result. Okay, and now I open the initial meshing. Okay. Now you will see that if I show from the top here, okay. Now if I show from the top here, inside the box, the meshing is different already. All focused already. As you see here, all focused already. All is very nice already inside the box. I want to highlight here is only inside this box, this toolbox. This is the toolbox. The other ones is still normal, but inside this toolbox is lastly different already. Okay. So now I move it back. I give you, then you see, you will see that inside this is the two local initial mesh regions, and inside this region, this is the without local initial mesh. That is still normal. And this is the after local initial mesh. This is quite that is quite more smaller already, the box, quite more refined already. So I can conclude that this one is more, have the better result, better energy result come out is compared with this one. Okay, now my meshing is done already. I want to show you about the results. Okay, I just show it the normal result. And that is, I load the full result. So from this full result, this is all I enhanced this result by using all the three enhancements: the curvature enhancement, the fluid cell, the partial cell, full cell enhancements, and the narrow channel enhancement. And this is the cut plot. This is the meshing of the very complete and the optimum result. as you see here, this is the optimum result. That is considered as a very nice result already. And by using these results, I can create I can see the temperature. Okay, done. And even the fluid flow, the direction of the fluid flow. Okay, done. Oops. I just manage it first to make you see more clear about this result. And this is the result. I will see here from the top here. You see that the air will flow into this one, the electronic rod from the inlet here, and flow across the electronic components and flow out from the fan. Need to see it clear. Flow in from the inlet here and across the electronic components and flow out from the fan. And flow out from the fan here. I will see here when this air will flow across the electronic components, the temperature of the fan, this color represent the temperature from the region here. The temperature of the air will increase and increase, and at the around this one outlet here, the temperature is around 50 degrees Celsius already. From the inlet of 25 degrees Celsius to the outlet of around 50 degrees Celsius. Okay, so this is the results of this study. I hide it. And now the last chapter, I want to focus on the transfer boundary. Okay, actually transfer boundary is we can just focus on study on one component only, but not all the components. We can only just need to study the one components. Okay, but not wasting the time. I want to study this one, the heat sink. And you see this is the result of the transfer boundary. All the other components I just hide it already and no study already. I just focus only the results shown in this heat sink only. Other things is not study. So this is very nice method to let us to cut the times, because the calculation of the flow simulation calculation is only calculate this area only, but not all the area. So from here, I just I just hide all the others component only, so that only show this fan and this heat sink only. Okay, from here, inside the flow simulations, the input data here, you see they have I minimize all here to let you see more clear. And you see here there is a transfer boundary conditions. Okay, I insert the transfer boundary conditions. I can transfer all information. Okay. Next. Then it will ask for the result of the transfer boundary. I choose the result of just now. Just now I show you the final result. Okay. Then I click OK. Then you will see that now I want to make this one. This is the area of the calculations, the region of the calculations. I just minimize it. Okay. I just minimize it to only calculate let it only calculate my heat sink only. Hey, now you will see that. Okay. Okay. Now you see that our calculate area will only focus on in this area only. There is no more other focus. Only focus on this area only. And after that, you will see that. Sorry, it's need sometimes. And after I load the result, I load the result first. And after I load the result, okay. After I load the transfer boundary results, this is the result after I generate out the. This is the result after I calculate it. After I solve these problems. Okay, you will see that. You only focus on this way. Okay, you see that. Now you will see the focus the focus on the study, the meshings will only in this boundary only. The other ways other than this boundary didn't have any meshing. It means that there is no solve or calculation in all this area. So the problem come out already. If they didn't cover all the areas, how they know the air that flow through this area? The air that flow through this area, like the air that flow in this direction to this heat sinks. Now this is a very good condition. Because this transfer boundary, it will import the data from just now. Just now I insert the transfer boundary, right? I do it again. You will see that it will import the result file from another result file. Import the result information from other result file. I import just now I import from the just now I complete ones. And after I click next, because this need a lot of time. After I click next, you will see that sorry, this take need a bit time, need around 10 to 20 seconds to let her to generate out the result. I want to focus here is you can study the individual electronic components rather than study all the electronic components. Because you study all the electronic components, you need to waste a lot of time to waste the calculation in all the other electronic components. However, now let's say if now I don't need to study this heat sink only, I don't need to study all the other electronic components. I just need to study the heat sinks and focus on it only. Let's say I have the 2 million of the cells, 2 million of the, my computer can support 2 million of the meshings. Now I can choose, I want to locate all these 2 million of the meshings in the world's 3D models, or I just locate the 3 million of the meshing inside this heat sink only. I can choose it. If I locate on all the 2 million meshing in this heat sinks, I can generate out the more better result, all better and more accurate result. If I compare to I locate the all 2 million of the meshing to the world's 3D models. So this is a very nice feature and very nice function for flow simulation, called as a transverse boundary conditions. Okay, so this is, as you see here, this is the result of the transfer boundary conditions. This on, as you see at the left side here, the flow simulation only will show the result of this boundary only. The other boundaries, no result will come out. Just now this is the flow trajectory. The result I showed at the flow trajectory. I will see the air will flow at this region only. The air will flow from here, the right, to the air, to the direction of the fan. And at here, this is the meshing. The other place is not meshing. Only this, the boundary here has the meshing only. The study region, our focus study region has the meshing only. And here, this is the result of the cut plot of the study. The other place didn't have the study, only this one's the region had the cut plot study only. Only this region will show the cut plot study only. This is the study of the temperature. As you see here, the temperature inside the heat at the heat sink area is very hot. It's around 66 degrees Celsius, and the other place is very quite cool if compared to the area of the heat sink. Okay, so now this is my presentations of my webinars. So you have any problems? If you didn't have any problems, then I will stop my presentation now. I will finish my presentation now. So thank you for your listening and for your listen to my webinars, and thank you very much. Thank you. So if you have any problems and any problem about flow simulations, you can see our website. Our website is CADVision. Our website is www.cadvision.com, and this is our website, SolidWorks Simulation. If you got any problems, you can ask any technical problem about these flow simulations, to our website, inside our website, or call us. Okay. So again, my name is Johnson. My name is Johnson Yap, Applications Engineer from CADVision Sendian Berhad, and I am ready to answer all your questions if you call our companies. If you call to our company for technical support. So thank you very much, and goodbye.